Let's get started. So welcome back. I hope you had a nice enough break. But now we need to get back to the semester 2 work. Before we start with the new chapter on differential equations, there's just a little bit of admin we need to get through. So firstly, the remaining tests for the year. So we're going to have class test 3 on the 11th of August. That's pretty soon, by the way. Couple weeks. Okay, then the class test 3. Class test 4 on 15th September. Class test 5 on the 27th of October. Please make a note of these and check with your other modules if there is a clash. Okay, so you got your MATH162, your physics, engineering, all of that stuff. Please check if there's a clash on the same day. I might be able to move the maths to another day in that week. Probably not another week. Okay, so if this is scheduled for the Tuesday and you have a test on the same day, I might be able to put it on the Wednesday, right? Depending on your different schedules. So please check that. As soon as you get your other tests, check with this, and then let me know if we need to move things around. Okay. If there's a major clash, then we might have to write on the Saturday, but hopefully these dates are fine. Yeah. All of these will be Tuesday for now, but we can move them around. Okay, then the scope, just so that you can start thinking about what's in these tests. So for class test 3, okay, this will be on differential equations. Okay, so that will be the stuff from this week and next week. Okay, differential equations. And then the second part will be on polar coordinates. Okay, so that will be done in the 3rd week. And then the class test 3, that will then be in the 4th week. Okay, class test 4. Okay, this will be on sequences, series, and Taylor series. Okay, so that will be after another 3 or 4 weeks. We'll have the class test 4. And then on the last day of lectures, just before your exam start, we're going to have class test 5. And that will be on your exam scope. Okay, so whatever's in the exam, that will come out in the class test 5. So your final exam will be 100 marks on everything. Okay. So I'll put a more detailed scope later on, like which smaller sections, to leave out, which ones to put more emphasis on. But broadly, it will cover everything this year. Most of it will be on the later parts of semester 1 and semester 2 work. And then about 25 marks will be on the integration stuff we did at the beginning. Okay. You know, the U substitution, by parts, all of that stuff. That will be about 25 marks. And then the 75 marks will be the rest of the applications, and then the stuff from semester 2. Okay, so the class test 5 will be on the same scope, but just half as much. So in the exam, if I give you 2 questions on integration by parts, then the class test 5 will have 1 question, right, to make up for the half. But it will cover everything. So this will be great practice for the exam. Also, whatever you get for this is a very good indicator of what you'll get in the main exam. Its questions are the same, right? Integration by parts in class test 5, integration by parts in the final exam. Complex function question in the test, pretty much the same thing in the exam, right? I'm not going to come up with whole new questions for both. Right, just change the numbers a bit, change an X to a Y, you know, change it up enough. Okay, so if you get 80% in the class test 5, a very good chance you'll get that for the exam as well. Right, of course, there's exam stress and all the other exams to worry about, so, you know, maybe not the same, but if you pass this, you're fine. Okay, guaranteed you'll be fine. If you fail this, you're not fine. Okay, then you've got a lot of work to do before the main exam. I think it's about 2 weeks they give you from end of lectures to start of exams. So from your results here, you have about 2-3 weeks, and then you write the proper main exam. All right. Any questions on that? Oh, good. Okay. We did the student review for first semester. I think 2 or 3 of you got Dean's commendations. Are you here? Did you see that in your results? Not yet. Okay, it might come up later. But if you look on Student Central for your results, it's got all the modules where it has that semester 1 headline and semester 2 headline. You'll see there in blue Dean's commendation. Okay, that is very, very good to get. Only about 10 or so in the whole degree get that. So 3 students here got that. So very well done. If you do see that, please make sure you put that in your CV. Okay, it's very, very good to get that. Again, only about 10 in the degree get it. So if you have that on your CV, it's really good for your, your job applications to have their Dean's commendations. Okay. If you didn't get it in semester 1, you can try get it for semester 2. I'm not too sure about the requirements, but I think all of your modules have to be passed at least 75%. And then your final weighted mark, I think, has to be above 80%. And then you get your Dean's commendation. I think there were 2 or 3. I'll check that. Okay. So that's it for the major assessments. The quizzes continue as normal. So no quizzes this week. Okay, so you had your free break now. That's double period on the Tuesday. Next week, that double period will be for tutorials and quizzes in DC, same as last semester. Okay, so Tuesdays will be the tutorial. Then you have a little break, and then I'll see you again at this time. Okay. And then I'll see you again on the Thursday at the end of the day. Okay, I'm not too happy with that time. It's like 2 o'clock to 4 o'clock. Not great. I'll see if I can move it so we don't have it right at the end of the day when everyone's tired. But for now, it's kind of fixed, 2 o'clock to 4 o'clock. Okay. If you do have free time in your schedule, let me know. I know some of you do chemical, some do civil, it's all different timetables. But if you can find a double period somewhere else in the week, maybe we can move some things around. Okay. Because having maths at the end of the day is not great, right? You're tired, I'm tired. So let's see if we can move that. If not, it will have to stay, right? 2 o'clock to 4 o'clock. Okay. Any questions on the admin stuff? All good. Okay. Let's start with the work for today. Okay, so a new chapter, differential equations. Quick show of hands. Who's doing electrical engineering? A few. Okay. You'll be seeing this every semester until the end of your degree. Okay. So please put a big star next to this. So the other ones, you will see some of this. So civil engineering, you'll see a little bit of this. Chemical, you'll see a little bit. But electrical engineers, every module from now till the end of your degree will have some form of differential equations. Okay. So in circuits, signals, all of that, you're going to have this. Okay, so others, you're a little bit luckier, but please put a big note there if you are doing electrical. Okay, so first thing, what is a differential equation? Okay, a differential equation you will see this abbreviated as DE. So if you're watching other YouTube videos and so on, If they say, oh, we're going to be solving this DE, they mean differential equation. Or if you have a set of differential equations, you say a set of DEs. Okay, it's abbreviated like that a lot of the time. Okay, so differential equation, or a DE, is an equation it's a pen. Yeah. Is an equation involving a function and its derivatives. Okay, so whenever you have some sort of equation that involves a function, whatever it might be, again, for the electrical engineers, it will be like the voltage or the current or something like that, and its derivatives. So as an example, let's say we have 3y double prime plus 3xy prime equals sine of y. Something like that. This is a differential equation. We see that it's an equation, obviously, and we've got this function y and its derivatives. There's y prime, there's y double prime. That makes this a differential equation. Yeah. Now we get two types of these in general. We're only going to be looking at the first type. The second type you'll look at next year, and that is an ODE and a PDE. So two types. So number one is an ODE. This is an ordinary differential equation. Okay. But again, a lot of times people will just speak about the abbreviation. So if you're looking in books and videos and so on, they might just say ODE, right? But that means ordinary differential equation. We just simplify it as ODE. So an ODE is where this function and its derivatives is a single variable function. Okay, so this could be y of x, f of t, something like that. It is a single variable function. And then on the other side, we have a PDE. This is a partial differential equation. Okay, so here the function is not a single variable function, it is a multi-variable function. Yeah. For example, we might have y is y of x and t. Yeah. Maybe it depends on position and time. If that is inside a differential equation, then it is a PDE, a partial differential equation. Now, we're not going to be looking at any of those, okay? For that, you need to take next year's module on multivariable calculus. And then after that first semester, then you'll be looking at these quite a lot. Okay, with functions of multivariables, so derivatives with multivariables, integrals with multivariables, and differential equations with multivariables. Okay, that comes next year, next semester, second semester. Okay, so here, please put a big box around ODEs. Those are the only ones that we're going to be looking at for this semester. Okay, so if you're looking online again for other examples or you're looking at videos, if they mention ODEs, that's what you need to be looking at. If you see anything with PDEs, you ignore that. We're not going to be looking at that at all. Okay, now there's some more terminology involved. Not too much, but we do need to know what these words mean. So just some more terminology. Okay. Number 1 is the order of a differential equation. Okay. And again, we're going to abbreviate it DE. You know that means differential equation. So the order of a differential equation is the highest order of the derivative. Very simple. We look at a couple examples. You'll get it right away. So example number 1, y prime is equal to 3x. We see that this is a differential equation. It's an equation of y and its derivatives. And we see that the highest order derivative is y prime. It is one derivative. So this is called first order. There's only one derivative. Okay. And then another example, y double prime squared equals 3xy prime. Okay. Again, this is a DE. It's a function. It's an equation of y and its derivatives. Here we've got y prime and y double prime, but the order is always the highest. So we've got y prime and y double prime. Y double prime is the highest, so we call this a second order. Okay. Whatever the highest is, that's what we use. If we had something with y triple prime, then that would be third order. 4 derivatives, that makes it fourth order, and so on. Yeah, again, whatever the highest one is. Okay, and then number 2. DE, again, differential equation, is called linear if the function and its derivatives, you must check for both, appear linearly. So what does that mean? Well, we know things that are non-linear, right? Like a parabola, that's non-linear, cubic is non-linear, exponential is non-linear, and so on. So linear is just some function of x times y. So any function times y. But the important thing is that y must be linear. It can't be y squared. It can't be e to the y or cos of y. All of those are non-linear. So we could have something like this. Maybe some function times y prime, some other function times y double prime. But again, y and its derivatives only appear linearly. There's no y squared or cos y or anything like that. So let's have a look at some examples. So we have y double prime plus 3xy prime plus 4y is equal to 0. We want to check if this is linear or not. So let's check for y and its derivatives. So y over there is just 4 times y. Okay, no y squared, no y cubed, nothing funny like that. So that part is linear. That's fine. Y prime, again, it's just 3x times y prime. It's not y prime squared or anything like that. So that part's linear. And then y double prime is just by itself. So that is also linear. If all of those are linear, then the whole thing is linear. So this is linear. So we check each one to see if they appear linearly in y and its derivatives. Okay, let's check another example. So we have y prime plus 3y squared equals cos x. Okay, so y prime, the first one there, that is linear. It's not being squared or anything like that. So that's fine. That was linear. But we see the next term is y squared. That is definitely not linear in y. So immediately one of them fails to be linear, the whole thing is then non-linear. One more example. Y prime squared minus 3e to the y is equal to 3x squared y. Y prime squared, that is definitely not linear in y prime. So the first one's not linear. So immediately the whole thing's non-linear, but let's check the other ones. E to the y, that's definitely not linear. The last one, 3x squared y, that is linear. Okay, that doesn't matter. The first one was non-linear, so automatically the whole thing is non-linear. Okay. Any questions about linear versus non-linear? Okay, pretty clear. You just go through the terms. As soon as you see something non-linear, immediately whole thing's non-linear. Okay, and then just a note. Like I said earlier, we're only going to be focusing on the ODEs, the ordinary differential equations. We'll make it a little bit easier. We will only focus on first order ODEs. Okay, now they might be linear, they might be non-linear, but they will be first order. So we will focus on linear or non-linear. Okay, it's not going to be super easy, so we can include both of those. So we'll focus on linear or non-linear first order ODEs. Okay. Later on, not this week, later next week, we will be looking at some second order differential equations, but that will be a very small case. Okay. So for that, we're going to be using the Laplace transform. Remember that from a while ago. So we're going to be using the Laplace transform to solve the second order ODEs. Okay, and again, electrical engineers, you're going to be seeing that a whole lot. Laplace transform with differential equations and Fourier transform with differential equations. Every semester until the end of your degree. Okay, but for the rest of us, we will only focus on the first order. Okay, so since this is first order, we can write it in a very specific way. We can write it as y prime is equal to f of x and y. So we know it's first order, so that means there's only one derivative. So whatever that is, we leave that on the one side. Okay. So the single derivative we leave on the one side. And then everything else, whatever it is, we push that over to the right-hand side. It could be linear, it could be highly non-linear, whatever mixing going on, whatever it is, we push that to the right-hand side. Okay, and this f of xy, that could be quite complicated. Okay, but whatever it is, we leave it on that side. Okay, and this will be the standard form that we're going to be looking at today. Okay, a little bit more terminology, and then we'll get into the actual calculations. Okay, so solving a differential equation. Okay, so what does it mean to solve a differential equation? So solving a differential equation is the process of finding a function or functions, there could be more than one, that satisfy the equation. Okay, so you got yourselves a differential equation. The act of solving it is finding a function, let's say y, that if you substitute it into the left-hand side and the right-hand side, you end up with left-hand side equals right-hand side. Okay, so it satisfies the equation. So in other words here, left-hand side equals right-hand side. So we'll have a look at a very simple example. So example, show that y equals e to the 3x is a solution, right? If you're solving something, you call that a solution. So show that y equals e to the 3x is a solution to the differential equation, and we have it as y double prime minus 2y prime equals 3y. So we've got a differential equation. We have something that is possibly a solution. We want to check, is this a solution? So this is a solution. If we substitute it into the left-hand side, we get some value. We substitute it into the right-hand side, we get some value. If those are the same, then it satisfies the equation. So let's check. Left-hand side. So that's going to be y double prime minus 2y prime. So we've got our function, we've got our left-hand side. Let's substitute and see. So this is y, so y double prime. That's going to be two derivatives. So we take the 3 down, we take another 3 down. So that will be, was that second derivative? Checking you're not sleeping already. What is that going to be? 9. Yes, thank you. Okay, minus, and then 2 times the first derivative. What will that be? 6. Good. Okay, and then we can simplify this. 9 minus 6. Okay, so we get that for the left-hand side. Now, for this to be a solution, it should also match up with the right-hand side. So the right-hand side here is just 3y. But y is e to the 3x, so we can substitute that in very easily. And that's fine. Yeah, so it works. If we substitute it into both sides, they're equal. So that means y equals e to the 3x is a solution to the differential equation. Okay, and I emphasize a solution, not the solution, because there could be more than one. Again, look at the thing here. So solving a DE is the process of finding a function or functions. There could be more than one solution. So is a solution to the differential equation. Okay. Any questions so far? Pretty simple. Let's now get into the calculating. Okay, so now we actually want to solve these differential equations. So in general, solving differential equations is very difficult, sometimes impossible to do, but under certain situations, they can be solved. And we're going to look at the different cases in which we can find a solution. So in general, these are very difficult, sometimes impossible to solve. Okay, but we will look at some cases that will help. Okay, so given some differential equation, if we can make it look like one of these different cases we're going to be looking at, then we know how to solve those. Okay, so again, given this right-hand side here, over there, depending on what this looks like, it could be case 1, case 2, case 3, something like that. Let's say we can make it look like case 2. Then there's a method or an algorithm that we can follow to solve it. Maybe we can make it look like case 1. Then there's another method or algorithm we can use to solve it. Okay, so the whole idea is, given whatever this mess is, we make it look like case 1, case 2, case 3, and then we know how to deal with that. Okay, if it's not one of those cases, we're going to have to try something else. We're going to see that next week. Or if that doesn't work, there's another method, but we can only use that at the end of the year. Okay, so it's all connected this semester. But for now, there's going to be 3 basic cases that we're going to look at. Okay, so the 3 basic cases. Okay, and each case comes with its own method that you can use to solve these. So case 1 is if we have a separable differential equation. Okay, so that's the name for the case. So a differential equation can be separable or not separable. So if it is separable, then we can use case 1. If it is not separable, then you have to look at case 2 or 3. It's like a yes-no type of thing. Is it separable? We can do case 1. Otherwise, try something else. Okay, and then the method used to solve this is called separation of variables. So that's the method that we're going to use. So let's go through it for our general differential equation. And then I've got 5 examples. Okay. So for a differential equation to be separable, it must be of this form. So we have y prime is equal to f of xy. Remember, that was the general one. Now this right-hand side, if we can split it up into 2 parts, one part with x and one part with y, then we call it separable. So we ask ourselves, can this be split into g of x times h of y? And that's a yes-no question. Can you do it? Can't you do it? If you can split it up, it's separable, we can use this method. If you can't split it up, it is not separable, you can't use this method. So the question, can you do this? Okay. Now, if you can, then we're going to use this to try and solve it. So this y prime, we're going to write it a little bit differently. You know, we can write it as y prime or dy by dx. So it's a little bit of notation change, but it's not too bad. So dy by dx is g of x times h of y. Now we're going to do a little bit of rearranging or separating. Everything with y we're going to take to one side. Everything with x we take to the other side. That's the separation part of this. So h of y, that's a y term. We take it over to this left-hand side. And the g of x, that's an x part. We're going to leave it there. dx, that's an x part. We're going to take that over. Now this almost looks like an integral. We're just missing the integration sign. So let's put that in. And don't forget, whenever you do an integral, you've got yourselves a plus c at the end. Okay, so from a derivative equation, a differential equation, we now get ourselves an equation with 2 integrals to solve. Okay, so we're going to solve both of these integrals. And then if possible, we're going to then solve for y. Sometimes that left-hand side is too complicated, then we just leave it. Other times we can solve for y. So next step is to solve the two integrals. And if possible, we're going to try and solve for y. And in my previous email, I put a big warning there about the integration techniques coming up. Right? You see here, we've got two integral problems to do. Now, the problem is, there's two of them that we need to solve, right? We got one on the left, one on the right. Let's say the left one you can solve. That's fine. But on the right, you forgot U substitution and you can't solve that. Right? Then how do you continue from there? Right? You can't solve the one side, now we can't solve for y. Because we're going to have something with y equals an integral and you don't know how to do it. You're stuck, right? Okay. So it's very important that you go over all of your integration techniques. Because previously the problem was just one problem, do U substitution or integration by parts or partial fractions. Now it's twice as bad. You got one on the left, maybe that's partial fractions. The one on the right, maybe it's integration by parts. It's a whole mess of things going on. So it's very important that you know all of your integration techniques because any of them can show up on this left side and this right side. Okay. So just a note. All integration techniques. Okay, because again, we don't know what these functions are. They could be anything. Maybe h of y is a quadratic. We have 1 over some quadratic. You have to complete the square, do partial fractions, something like that. Right? Again, it depends on what's given there. Okay, so again, I remind you, go over all your integration techniques because you don't know what's going to come up with these two sides. All right. Any questions on the method before we get to the examples? Oh, good. Okay. So let's have a look at some examples. Okay, so number one, we have y prime is equal to x squared over y squared. Okay, nice and simple. Now, the questions in the test and the exam and so on aren't going to say solve the separable differential equation. I'm not going to tell you which one it is. I'm just going to have a list, solve these. So the first thing you need to do is figure out what type of equation it is, and then, okay, which method to use, and then you can solve it. So here, we know it's separable because it's under the section, but always think to yourself, you have to check before. Okay. So we look at this and we ask ourselves, is this separable? Yes or no? Yes, it is, because we can split it up. We can write this as x squared as one term and 1 over y squared as another term. Now, this question is very simple to split it up. We'll see the next one, might not be so clear on splitting up. Okay, but here, definitely separable. We can use this method. So let's do that. Okay, so anything with y, we're going to take to the left side. Anything with x, we're going to take to the right side. Okay, now we're missing our integral signs, so let's put those in. And then after we're done with the integration, we have a plus c. So let's put that in. Now, straightforward. Two integral problems. One with y, one with x, but we just treat them as two separate problems. So the first one, that's going to be 1/3 y cubed. We don't need to worry about plus c. We already did that. We've got it on the side there. Next one, 1/3 x cubed plus c. And now the last step, if possible, let's try and solve for y. Here we can, pretty straightforward. So let's multiply through by 3. And now this constant c is a constant. a constant times 3 is just another constant. So instead of calling it something else, I'm going to say C becomes 3C, and then I'm just going to rename it immediately back to C. Okay. So here, C, this became 3 times C because of multiplying the 3 over, and immediately I renamed it back to C. All right, you could have called this B and then renamed it back to C. But it saves us from having a whole bunch of constants piling up with that plus C. Okay, so adding a constant, multiplying a constant, again, we immediately rename it back to C. Now we've got cubed, we just take cube roots. And we're done. There's our solution. In fact, this is infinitely many solutions because of that plus C. C can be anything. It can be 0, it can be 1, a half, pi, doesn't matter. We get a whole family of solutions for this differential equation. And that's the technical name. It's a family of solutions. Right, think back to when we did antiderivatives. We had a whole family of antiderivatives, capital F of x plus c, right? Same idea here. We have a whole family of solutions for the different c values that you can choose. Any questions for this one? Yeah, pretty straightforward. Okay, let's have a look at number 2. So we have y prime is equal, xy prime is equal to y plus x squared y. Okay, now just looking at this as is, can't really tell if it's separable or not. Right, we've got a mix of x and y terms. The question is, can we split this into g of x times h of y? Yes, we can. A little bit of algebra first, though. So on the right side, we have a common factor of y. Let's take that out. Okay. And then let's divide through by that x. Okay. So now it's very obviously separable. Okay, so there might be some stuff you have to do first before you can clearly see if it's separable or not. Okay, so let's do the separation. So y prime, we can write as dy by dx. And then we have y, and then all the stuff with x. So anything with y, we're going to put onto the one side. Everything with x, we're going to put onto the other side. Okay. Now we're missing the integral sign, so let's put that in. And when we're done with the integrals, remember we have our plus c. Okay. Now we have 2 integral problems to do. We can just do them separately. So the first one, integral 1 over y dy, that's the natural log. And on the other side, we have the natural log of x plus half x squared plus c. Now, can we solve for y? Yeah, we can. We can do the exponential on both sides. So we're going to have y of x is equal to e to the natural log of x plus half x squared plus c. Okay, we can simplify this a little bit more. Let's split up the exponential into 3 terms. So we're going to have y of x is equal to e to the natural log of x. Okay, remember these are inverses, so we know what to do there. E to the half x squared and e to the c. Okay, e to the natural log of x, they cancel, so we just have x. The other one, that just stays. Okay, and this e to the c, like we did before, a constant times a constant is a constant. E to the constant is also a constant. So we could rename this to just c. That would be fine. Like that. But typically, for whatever reason, e to the c is given the name a. It's just the name, doesn't mean anything. So you can call it c, you can call it a. That's up to you. Okay, but if you're looking online and suddenly the C becomes an A, it's just a convention. Okay, so don't worry about how did this E to the C become an A. It's just a renaming. Okay, but that is typically done. If you have something with exponentials, that thing in front there, that constant, we just call A. Okay, but you use whatever you want. All right. Any questions for this one? Okay, pretty simple. And then the last one for today, number 3. We have y plus 1 minus x, y prime is equal to 0. And we have an extra bit of information. We want a solution where y of 0 is 1. So this is a differential equation plus an additional bit of information that we call an initial condition. So this is some extra information called the initial condition. We call it initial because you can think of this like physics. You know, you throw a ball, you have an initial velocity and initial position. It's whatever happens at t equals 0. Same idea. Whatever happens at y equals 0. That is your initial condition. You can think of this as like the initial position. So at t equals 0, you have an initial position. At x equals 0, you have an initial y. Exactly the same idea. So whatever that extra info, that is called an initial condition. And together, the differential equation and the initial condition is given the name initial value problem. Okay, a lot of names, very simple thing. And like with the other things, they all have their own little acronyms. This is called an IVP. Yeah, so mathematicians love naming things. Here's another name we need to learn. Okay, so again, differential equation plus initial condition, that is an initial value problem, or an IVP. Okay, so we're going to solve this differential equation as usual, okay, like we had above. But now right at the end, we're going to substitute this initial condition, and that will allow us to solve for this unknown constant. So the initial condition allows us to solve for the unknown constant c that we always had. Okay, so let's go through this one quickly. Very simple. Let's take all the stuff over to their proper sides. So we're going to have y plus 1 minus x y prime is equal to 0. Let's rearrange. Okay, y prime we can write as dy by dx. Let's take the y stuff to the left, the x stuff to the right. Let's add in our integral signs. And remember, we need a plus c. Okay, so integrating, very easy. First one, natural log with the minus sign there. Next one, natural log, again with the minus sign, plus c. Let's multiply through by minus 1. We're going to get a minus c. I'm immediately going to rename it to just c. Okay. Again, put a little star there. That's just the renaming. So minus c, I just call plus c again. We can do the exponential on both sides. Okay, so we still got that plus c there. We can split this up into two parts like we did before. And then the e to the c, we can just rename back to c. Okay, or you can call it a, doesn't matter. Again, this is some unknown c. We don't know what it is. So this gives us a whole family of solutions, but we have an initial condition that will allow us to fix a value of c. So y of 0 is 1. We can substitute that in. So what does that mean? It means whenever x is 0, y is 1. Okay, very easy. C is just 1. So instead of having a solution with some unknown c, the initial condition gives us one solution where c is 1. A different initial condition will give a different value of c. So we get y of x is 1 minus x, no unknown constant. Okay. So it's not a family of solutions like we had before. It's just one solution, this one. Okay. Any questions for this one? You're all good. Okay. Let's do one homework problem just to try out, and then we'll carry on Thursday. Sorry, not this one. We did that. Okay, so we have a differential equation and an initial condition there. And then maybe something a little bit more difficult. Yeah. And then one not so difficult, but a little bit challenging. Okay, so all of these are initial value problems. And all of these are separable. So the first two are pretty obviously separable. The last one, just remember that exponential, we can split into two parts. Yeah. So that is actually separable. Okay, any questions for the homework? Oh, good. Okay. So on Thursday, we'll carry on with a few more examples, and then we'll look at homogeneous differential equations and linear differential equations. Okay, so if you want to get ahead with the work, it will be homogeneous and linear for Thursday.